Every star you have ever seen is a memory. The light from Proxima Centauri left 4 years ago. The light from Andromeda left 2.5 million years ago. The light from the cosmic microwave background left 13.797 billion years ago. The night sky is a mosaic of different nows stitched together by one number, the speed of light. And tonight that number is going to stop being about speed at all and start being about something far stranger. Before we get into it, subscribe to Sundown Science. Find a position you can stay in. Dim the lights if they are still on, and get comfortable, because tonight's journey is unlike anything you have heard before. And once you understand what this number is really protecting, you will see why it has never been broken and why it should never be. Part 1. The wall everyone knows about. Let me start with the number itself, because you should know exactly what you are looking at when I tell you it is the most thoroughly defended boundary in physics. 299,792,458 meters per second. We have known this number since 1972, when a research team at the National Bureau of Standards measured it to within 1.1 meters per second. 11 years later, in 1983, the world's metrology bodies decided the number was so precisely known and so fundamental to physics that they did something extraordinary. They stopped measuring it. They defined it. From 1983 onward, the speed of light is exactly 299,792,458 meters per second by international agreement, and the meter, the unit you have known your whole life, is now derived from the speed of light. The meter is the distance light travels in 1/299,792,458 of a second. The unit you measure your kitchen counter with is now downstream of the speed of light. That is how seriously physics takes this number. You probably know the engineering version of why nothing can travel faster than light. As an object accelerates, its kinetic energy goes up, but at relativistic speeds, the energy required to accelerate it further does not go up linearly. It climbs along a curve called gamma. At half the speed of light, gamma is 1.155. At 90%, gamma is 2.29. At 99% of C, gamma is 7.09. At 99.9%, gamma is 22.37. At 99.99%, 70.71. At 6 nines of C, that is, 0.999999 of C gamma is 707.1. To accelerate 1 kilogram, the mass of a small bag of sugar, to that velocity, you would need an energy of roughly 6.4 times 10 to the 19th joules. That is more energy than the entire annual electrical generation of the United States, deposited into 1 kilogram. And the closer you push to C, the more energy each additional meter per second of velocity costs you. Reach C exactly, and you would need infinite energy, which is to say, you cannot reach it. That is the textbook version of the speed of light wall. And it is correct. It is what physics teachers say. It is what you might have read in a popular science book somewhere. And tonight, I am going to tell you that it is also incomplete. There is a deeper reason no spaceship has ever exceeded the speed of light. A reason that has nothing to do with how much fuel you can pack into the tank. The deeper reason is geometric. It is about the structure of space and time itself. And once you see it, you will understand that the speed of light limit is not a wall the universe puts in front of your starship. It is the wall the universe builds around the very idea of a starship, around the very idea of cause and effect, of memory and prediction, of the question and the answer. So if this has you hooked already, take a moment. Subscribe to Sundown Science, because over the next 2 hours, we are going to walk through one of the strangest geometric proofs in physics. The one that tells you faster than light travel is not a speed problem at all. It is a logic problem. Drop a comment telling me where you are listening from tonight. And tell me, if you could break the speed of light tomorrow, what is the first place you would go? I want to know. Get comfortable. Find a position you can stay in. Dim the lights if they are still on. We have a long way to walk, and the destination is going to take some unlearning. Because here is what the equations actually say. The moment you start asking what really happens to the universe when you cross this wall, not to your starship, but to the universe itself, to its causal architecture, to the relationship between past and future, you will see why no engineer has ever broken it. Because no engineer has ever been allowed to. Part 2. The first crack. Let me ask you a question that, if you have not heard it before, will sit in your head for the rest of this video. Why is the speed of light the same in every inertial frame? I will say that again. If you are standing on a platform and a beam of light passes you, you measure its speed at c. If you are running toward the source of that beam at half the speed of light, you should, by ordinary arithmetic, measure its speed at 1.5 c. That is how it works for every other thing in your daily life. A car coming toward you at 60 miles per hour seems to be approaching faster if you are driving toward it. A baseball thrown at you while you walk forward strikes your glove harder than a baseball thrown at you while you stand still. Light does not behave that way. If you run toward the beam at half c, you measure the beam at c. If you run away from it at half c, you measure the beam at c. If you sit still, c. If you accelerate, c. There is no inertial frame, no observer anywhere in the universe who has ever measured the speed of light to be anything other than c. This is not a quirk. This is the most stubbornly confirmed fact in all of experimental physics. We tested it in 1887 with the Michelson-Morley experiment, expecting to find a frame-dependent variation, and we found nothing. We have tested it 10,000 times since, with progressively more precise apparatus. The speed of light is the same in every inertial frame, full stop. That is one fact. Here is another. Gravitational waves ripples in the fabric of spacetime itself. The kind LIGO detected for the first time in September of 2015 also travel at exactly c. We know this from the gravitational wave event called GW 170817 in August of 2017, when LIGO and Virgo detected a neutron star merger and the same merger's gamma-ray flash arrived at Earth at almost exactly the same time. The two signals had travelled 130 million light-years and arrived within 1.7 seconds of each other. From that, physicists were able to constrain the speed of gravity to equal the speed of light to 1 part in 10 to the 15th. That is 1 part in a quadrillion. The speed of gravity is c. Here is a third fact. The speed of any massless gauge boson, that is, any of the fundamental force-carrying particles that have no mass, is c. Photons, electromagnetism, c. Gluons, the strong force, in a sense that gets technical, c. Gravitons, which we have not detected directly, but which the theory predicts c. So the same number controls electromagnetism, gravity, and the propagation of changes in the metric of spacetime itself. 3 apparently unrelated phenomena, 1 shared constant. That is not a coincidence. That is a hint. The universe is telling you that c is not a property of light, the way the speed of sound is a property of air. The universe is telling you that c is something else, something deeper, something that light, gravity, and space-time all share, because they are all expressions of the same underlying structure. What is that structure? In special relativity, there is a quantity called the space-time interval. It is a way of measuring the distance between two events in 4-dimensional spacetime, the same way you might measure the distance between 2 points in 3-dimensional space. The formula has 4 terms. 3 of them are spatial, the differences in x, y, and z. The 4th is temporal, the difference in t, multiplied by c, then squared. And here is the strange thing. In the space-time interval, the time term has a minus sign in front of it. The spatial terms are positive, the time term is negative. That single minus sign is what separates the past from the future. It is what makes time different from space. It is what allows you to remember yesterday, but not tomorrow. If C were infinite, that minus sign would lose its meaning. The four-dimensional structure would collapse into a kind of Galilean block, 4 dimensions, all of the same character, with no causal arrow, no asymmetry between before and after. The universe would not know which way time flows because, geometrically, it would not have a way. So C, that finite number we keep measuring, is doing the work of holding the past and the future apart. It is the geometric expression of causality. It is the slope of a structure called the light cone, and the light cone is the universe's way of saying which events you can affect and which events you cannot. Imagine a flashlight. Right now, at this moment, point it straight up and turn it on. The light from the flashlight expands outward in all directions at C. After 1 second, it has expanded into a sphere about 300,000 kilometers in radius. After 2 seconds, 600,000 kilometers. After 8 minutes and 20 seconds, the sphere reaches the Sunday. After 4 years, it reaches Proxima Centauri. After 2.5 million years, it reaches Andromeda. That expanding sphere of light from this present moment is the boundary of what you can causally affect. Anything inside that sphere is part of your future light cone. You can, in principle, send a signal there. Anything outside that sphere is the elsewhere you cannot affect it, because no signal you send today can ever reach it. The cone is your causal sphere. Outside the cone, at this moment, is a part of the universe to which you do not exist. There is no version of the next minute in which you can change anything outside that cone. Now, flip the picture. There is also a past light cone, narrowing back from this moment, containing every event that could have affected you. Anything inside the past cone is something whose light or signal has had time to arrive. Anything outside the past cone is causally disconnected from your past. You have not heard from it yet, and you cannot have been influenced by it yet. This is the geometry of cause and effect. Future cone, past cone, and the elsewhere outside both. The slope of both cones on a spacetime diagram is c. And this is the part that nobody told you in school. The speed of light limit is not a wall around your starship. It is the boundary of the cone around your existence. Your existence as a coherent being depends on this boundary holding. Now think about what it would mean for a signal to travel faster than c. A signal slower than c stays inside the cone. A signal exactly at c rides the surface of the cone. A signal faster than c, what would that look like? On the spacetime diagram, it would exit the cone sideways. It would leave the future light cone and cross into the elsewhere. It would enter a region that, by definition, no causally connected event has any business reaching. 2 observers, both moving uniformly, both correct, both armed with stopwatches that have been calibrated to atomic precision, and yet they will not agree on what came first. In the next part, we are going to put a transmitter in their hands. Part 3, Minkowski's geometry. To understand what happens when you let 2 observers exchange faster than light signals, you need to understand what Hermann Minkowski did to the equations of physics in 1908. And to understand that, you need to know who Minkowski was. He was a German mathematician born in 1864 who taught at the Zurich Polytechnic in the late 1890s. One of his students was a quiet, distractible young man named Albert Einstein. Einstein was not, by Minkowski's reckoning, a particularly good student. Years later, after Einstein had become the most famous physicist in the world, Minkowski admitted that he had thought of him as a lazy dog who never bothered with mathematics. The lazy dog had, in 1905, published 4 papers in his spare time while working as a clerk at the Swiss Patent Office. One of those papers laid the foundations of special relativity. Another won him the Nobel Prize. Another sketched the equivalence of mass and energy. The fourth dealt with Brownian motion. Minkowski looked at the relativity paper, and 3 years later, in September of 1908, at a scientific conference in Cologne, he gave an address that has become one of the most quoted lines in the history of physics. He said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski had realized was that Einstein's special relativity was not really about clocks and rulers, it was about geometry. Specifically, it was about a four-dimensional geometric manifold in which space and time are unified into a single structure with a particular shape, and that shape determines everything else. The shape is called Minkowski spacetime. It is four-dimensional, but the time dimension carries that minus sign we talked about. That is what makes it pseudo-Euclidean rather than ordinary Euclidean 4 space, and the consequence of that minus sign is the light cone. In a Minkowski diagram, and you have probably seen one, even if you did not know that was what you were looking at, time is plotted vertically, space is plotted horizontally, and the trajectory of a particle through space-time is called its world line. A particle at rest traces a vertical world line going straight up the time axis. A particle moving uniformly traces a tilted world line. The slope of the world line is inversely proportional to the velocity. A particle moving at exactly c traces a line at 45 degrees because c is set as the natural unit. A particle moving slower than c has a steeper than 45-degree world line. A particle moving faster than c, if such a particle existed, would have a shallower than 45-degree world line. It would tilt more horizontal than vertical. The light cone, in this picture, is the surface traced out by all the photons emitted from a single event in all directions. It is the 45-degree double cone opening upward into the future and downward into the past, centered on that event. Inside the cone is the time-like region. Outside is the space-like region, the elsewhere. On the surface itself is the light-like, or null region. So the speed of light, in Minkowski's formulation, is not really a speed at all. It is the slope of a geometric boundary. Light is the special case of a particle that travels exactly along that boundary. Anything massive must travel inside the cone with a steeper world line. Anything massless must travel along the cone at exactly 45 degrees. Anything that travels outside the cone, anything with a shallower world line, would by definition be moving through the elsewhere. Now I want you to do something, because I think this is the moment in this video that, if it lands, you will remember for a long time. I want you to think about your own light cone, right now, at this moment. You are sitting somewhere, maybe in bed, maybe on a couch, maybe at a desk with a window in front of you. There is an event happening at the location of your body right now. That event is the center of your light cone. From this moment, an expanding sphere of light is rippling outward at c in every direction. After about 1 second, the sphere will have expanded past the orbit of the moon. After about 8 minutes and 20 seconds, it will reach the Sunday. After about 5.5 hours, it will pass Pluto. After 4.24 years, it will arrive at Proxima Centauri, the nearest star to the solar system after our own. After about 100,000 years, it will have crossed the disk of the Milky Way galaxy and be exiting into intergalactic space. After 2.5 million years, it will reach Andromeda. Anything that lies inside that expanding sphere, at any moment in your future, is something you can, in principle, send a signal to. Anything outside it is, at this moment, in your elsewhere. You do not exist for it. It does not exist for you. There is no causal contact possible between you and any event outside that sphere until enough time has passed for the sphere to grow large enough to include it. Look around the room you are in. Every object you can see is bathed in your past light cone. Light from those objects is reaching you now, because it was emitted in your past and has had time to arrive. Look at your hand. The light from your hand is reaching your eye after traveling about 1 nanosecond, because it had to cover the distance from your hand to your retina at sea. You are not seeing your hand as it is right now. You are seeing it as it was 1 nanosecond ago. Look at the wall across the room. You are seeing it as it was about 10 or 12 nanoseconds ago, depending on the distance. Look at the moon, if it happens to be visible. You are seeing it as it was 1¼ seconds ago. Look at the Sunday. You are seeing it as it was 8 minutes and 20 seconds ago. The sun could have exploded 6 minutes ago, and you would not know yet. The information has not arrived. Every photon arriving at your eye right now is older than every choice you have ever made about whether to look at it. The light from this moment, leaving you in every direction, is going out into a universe that does not yet know you have moved. This is the structure your existence is embedded in, a light cone tilted at 45 degrees on the diagram. Inside it, the universe that has affected you and the universe that you can affect. Outside it, the elsewhere, the part of reality with which, at this moment, you have no causal relationship. Now, with that picture in your head, ask the question we have been working toward. What if a signal could leave the cone? What if you could fire a photon, or some hypothetical superluminal particle, or some warp bubble apparatus, or some entangled state communication channel that did not exist, that exited the cone sideways, that entered the elsewhere? The answer, the strangest and least known answer in all of fundamental physics, is that you would not have built a faster radio. You would have built a time machine. And the rest of this video is about why. 2 observers, both moving uniformly, both correct. One on Earth, one on a starship, moving at 3/4 of C. Each of them with a hypothetical superluminal transmitter sitting on the desk in front of them. Each of them, in their own frame, sees their transmitter as a normal radio that just happens to send signals faster than light. In the next part, they are going to use them. Part 4. 2 observers disagree. There is a thought experiment, almost 120 years old now, that every physics student learns in their first course on special relativity. It is called the train and platform thought experiment, and Einstein himself used a version of it in 1905 to demonstrate the most counterintuitive consequence of his theory, the relativity of simultaneity. Picture a train moving uniformly along a track at relativistic speed. On the platform, you are standing still, watching the train go by. There are 2 lightning bolts. One strikes the front of the train, the other strikes the back. From your position on the platform, the 2 bolts strike at exactly the same moment. You are equidistant from both. The light from each bolt reaches you simultaneously, and you correctly conclude, based on the position of the strikes, the speed of light, and your timing, that the 2 events were simultaneous. Now move yourself onto the train. There is another observer, sitting in the middle of the train, moving with the train at the same relativistic velocity. The same 2 lightning bolts strike. But for this observer, things look different. The train is moving forward. The light from the front bolt has less distance to travel to reach the middle of the train, because the middle is moving toward where the front strike happened. The light from the back bolt has more distance to travel, because the middle is moving away from where the back strike happened. The light from the front bolt arrives at the train observer first. The light from the back bolt arrives second. Both observers measure the speed of light in their frame at exactly c. Both observers do their geometry correctly, and they reach different conclusions about which bolt struck first. The platform observer says simultaneous. The train observer says front bolt first, back bolt later. There is no master clock. There is no privileged observer. Neither of them is wrong. Simultaneity, it turns out, is not an absolute fact about events in the universe. It is a frame-dependent quantity. Events that are simultaneous in one frame are not simultaneous in another. There is no universal now. Now, I want you to understand that this is not a thought experiment we are making up to mess with your intuitions. The relativity of simultaneity is what you would find if you actually ran the experiment. We have run it in different forms hundreds of times. The data confirms it to absurd precision. In October of 1971, two physicists named Joseph Hafele and Richard Keating loaded 4 cesium atomic clocks onto commercial airliners and flew them around the world, once eastward, once westward, comparing them on return to clocks that had stayed at the U.S. Naval Observatory in Washington. The eastward clocks, after their flight, had lost about 59 nanoseconds compared to the ground-based reference. The westward clocks had gained about 273 nanoseconds. The difference was real, it was measurable, and it matched what special and general relativity together predicted to within experimental error. Time on the eastward planes had run more slowly. Time on the westward planes had run more quickly. There is no universal now, and we proved it with cesium clocks and Pan Am flights. If you have a phone in your pocket, you are carrying a relativity confirmation device. The global positioning system works by triangulating signals from satellites in orbit, each of which carries an atomic clock. Those satellites move at about 14,000 kilometers per hour relative to the ground, which means special relativistic time dilation makes their clocks tick slower than ground clocks by about 7 microseconds per day. They are also at about 20,000 kilometers altitude, which means they sit higher in Earth's gravitational well, and general relativistic gravitational time dilation makes their clocks tick faster than ground clocks by about 45 microseconds per day. The net effect is that the satellite clocks, without correction, would gain about 38 microseconds per day relative to your phone. Without that correction applied to every signal, GPS would drift by approximately 10 kilometers per day. By next week, it would be useless. Every GPS receiver in the world, including the one in your pocket, applies a daily relativistic correction of plus 38 microseconds. The relativity of simultaneity is not theoretical to anyone who has ever used a phone for navigation. In 2010, a team led by Chi-Wen Chu at the National Institute of Standards and Technology in Boulder, Colorado, set up 2 aluminium-ion optical clocks in their lab. They moved one of the clocks at about 10 meters per second relative to the other, that is the speed of a brisk walk. Then they raised one of the clocks by about 33 centimeters relative to the other. That is the height difference between sitting in a chair and standing up. Their clocks were precise enough to detect the time dilation effect of those motions. The clock at the higher elevation ticked faster by parts in 10 to the 17th. The clock that had been moved ticked slower by parts in 10 to the 17th. They measured general relativistic time dilation across 33 centimeters of altitude. They measured special relativistic time dilation at the speed of human walking. In 2022, a different team, led by Tobias Bothwell, also at GILA, the Joint Physics Institute between NIST and the University of Colorado, pushed even further. They measured the gravitational time dilation across 1 millimeter of vertical separation. 1 millimeter, the thickness of a fingernail. Across that distance, time runs at slightly different rates, and Bothwell's clocks were precise enough to measure the difference. 7.6 parts in 10 to the 21st. I want you to sit with that for a second. Time is not the same at the floor as at the ceiling. Time is not the same at the top of your hand as at the bottom. Time runs at infinitesimally but measurably different rates, at every vertical separation, in every gravitational gradient, in every relative motion. There is no universal now. There is only the local time at the location of each clock, and those clocks, when compared, do not agree. The physicists who study this for a living have a phrase for what relativity does to your everyday picture of time. They call it the breakdown of absolute simultaneity. And the way the breakdown is parametrized, the way you can write down the size of the disagreement, is by something called the simultaneity tilt. Two observers in relative motion have, at any moment, a slightly different idea of what counts as right now. If you draw a Minkowski diagram, the platform observer's line of simultaneity is horizontal. The train observer's line of simultaneity is tilted. The amount of the tilt scales as the relative velocity v divided by c squared. Even at orbital velocity, the International Space Station moves at about 7.7 kilometers per second, which is enough to circle the Earth in 90 minutes. The simultaneity tilt is real and present. It amounts to about 3.5 nanoseconds across one Earth radius, tiny, but not zero, and measurable in modern atomic clock experiments. At relativistic velocities, the tilt becomes large enough to put events in different orders for different observers. Two events that one observer sees as simultaneous, another observer moving fast enough relative to the first sees as separated by significant time, and not always in the same direction. If you are moving in one direction, event A precedes event B. If you are moving in the opposite direction, B precedes A. This is the architecture we are working inside. There is no privileged observer. There is no universal now. Different observers, all of them correct, will disagree on the order of events. Now, hold that picture, because we are about to do the strangest thing you can do inside this architecture. We are about to put a transmitter in the hands of two observers and ask what happens when they exchange a signal that exits the light cone. The moment you understand that two correct observers can disagree about which event came first, you are one step away from understanding why no signal in this universe is allowed to outrun the boundary between them. Part 5, Tolman, 1917. There is a textbook called The Theory of the Relativity of Motion, published in 1917 by the University of California Press. It is roughly 200 pages long. The author was Richard Chase Tolman. Tolman was 36 years old. He had completed his Ph.D. at MIT in 1903, gone on to teach at the University of Michigan and the University of Cincinnati, and was, by 1917, on his way to becoming one of the most respected theoretical chemists and physicists in America. He would later go on to do foundational work in statistical mechanics. He would help train an entire generation of American physicists. During the Manhattan Project, he would serve as a senior advisor to Robert Oppenheimer. But in 1917, he was finishing this textbook, and on pages 54 and 55, in a section he labeled almost casually an apparent paradox, Tolman did something nobody had quite done before. He took the relativity of simultaneity, which Einstein had introduced in 1905, and he applied it to a hypothetical device, a device that could send signals faster than the speed of light. Not because he believed such a device existed. He did not. He was making a logical point. He was asking, what would happen if it did? What he found, when he worked through the geometry, was a paradox so clean and so devastating that the argument he laid out has, in the 109 years since, never been broken. Every refinement, every challenge, every attempt to find a way around it has either failed or has reproduced the original conclusion in a slightly different form. Tolman's argument is one of those rare results in physics that stands as a genuine no-go theorem, and the no-go applies to anything that signals faster than c, regardless of how it does it. Modern physicists have given Tolman's device a name. They call it the tachyonic anti-telephone. The tachyon part is the Greek-derived word for fast. It is the technical name for any hypothetical particle or signal that moves faster than light. The anti-telephone part is what makes the name honest about what the device actually is. Because, as Tolman showed, a phone that sends signals faster than light is not a phone. It is the opposite of a phone. It is a device that lets you receive the answer to a question before you have asked it. Let me set up the apparatus carefully. because this is the central argument of the entire video, and I want you to be able to follow every step. You have two observers. Call them Earth and Starship. Earth is at rest in some reference frame. Starship is moving away from Earth at 3/4 of the speed of light. Both observers have the same hypothetical FTL transmitter. Call it any speed greater than c that you like. Let us say twice the speed of light for concreteness. Both transmitters send signals at twice c in the rest frame of the device. Each observer, in their own frame, sees their transmitter as a normal radio that just happens to send signals faster than light. Earth's simultaneity plane is horizontal in our diagram. Starship's simultaneity plane is tilted because Starship is moving relative to Earth at 3/4 of c. The tilt is what Einstein and Minkowski showed us. Different observers have different ideas of now. Earth, on its calendar, picks a moment and calls it time 0. Earth's clock reads 0. At that moment, Earth presses the button on the transmitter. The signal leaves Earth, moving at twice c in Earth's frame, in the direction of Starship. Starship is, let us say, 4 light hours away from Earth at the moment Earth presses the button. The signal, travelling at twice c in Earth's frame, takes 2 hours of Earth time to reach Starship. So in Earth's frame, the signal is received at time plus 2 hours. So far, so good. The signal travelled forward in time in Earth's frame and arrived at Starship 2 Earth hours after it was sent. That is what an FTL signal does in Earth's frame. There is nothing visibly strange about it. But now consider what happened in Starship's frame. Starship was moving away from Earth at 3/4 of c when the signal was emitted. Starship's simultaneity plane is tilted. The arrival of the signal at Starship is one specific event in spacetime. We can ask, in Starship's frame, what time it was when that event occurred. When you do the math, working through the Lorentz transformation that connects Earth's coordinates to Starship's coordinates, you find that the arrival of the signal at Starship occurred in Starship's frame at a time earlier than the emission of the signal at Earth. Not just slightly earlier, substantially earlier. The exact number depends on the velocity and the FTL speed. For the parameters I just gave, the arrival occurs about 2 3/4 hours before the emission in Starship's frame. That sounds impossible. It is not impossible. It is what the Lorentz transformation gives you when you plug in superluminal velocities. The emission and the arrival of an FTL signal are space-like separated. They lie outside each other's light cones, and for space-like separated events, different observers in different frames will, in general, disagree about their temporal order. Two events outside each other's light cones can be simultaneous in one frame, A before B in another, and before A in a third. That is not an exotic fact. That is the relativity of simultaneity, applied to events that the speed of light geometry has placed outside each other's causal contact. Now Starship, having received the signal, decides to reply. Starship presses its own FTL transmitter button at the moment of reception, which, in Starship's frame, is sometime we will call Starship time of reception. Starship's reply travels at twice c in Starship's frame, headed back toward Earth. Here is where the geometry locks in. In Starship's frame, the reply travels forward in time. There is nothing strange about it. It is a normal FTL signal in Starship's frame, the same way Earth's original signal was a normal FTL signal in Earth's frame. But in Earth's frame, once you transform Starship's coordinates back to Earth's coordinates, the reply does something extraordinary. It arrives at Earth at a time before time 0, before Earth pressed the original button, before the conversation began. The exact time of arrival in Earth's frame depends on the geometry. If you set up the speeds and distances I described, the reply arrives at Earth at approximately Earth time minus 4 hours. 4 hours before Earth pressed the original transmitter button, Earth, sitting at the desk, is about to do something. The reply is already on the console. I want to be clear about what I just said, because the temptation is going to be to assume I made some kind of mistake, or that this is one of those word game paradoxes that dissolves when you look at it carefully. It is not a word game. The Lorentz transformation, which has been confirmed to absurd precision by every relativity experiment ever performed, takes you from Earth's coordinates to Starship's coordinates and back again. When you assume an FTL transmitter and apply the Lorentz transformation, the geometry forces this result. The reply arrives at Earth before the original signal was sent. There is no error. There is no clock confusion. There is no, we just measured it wrong. The geometry of two inertial frames in special relativity, combined with a faster-than-light signaling device, places the arrival of the reply in the past light cone of the emission. The threshold for this, the velocity at which the geometry breaks causality, has a clean formula. If your FTL speed is u, and the relative velocity between the two observers is v, then the reply arrives in the past whenever the product of u and v exceeds c squared. That is, whenever v exceeds c squared divided by u, for an instantaneous signal, u equal to infinity, any non-zero relative velocity breaks causality. For a signal at twice c, the threshold relative velocity is half c. For modest superluminal speeds and modest relative motions, you get backward in time signaling almost immediately. What we have just walked through is not a thought experiment about strange edge cases. It is a direct algebraic consequence of two facts: that the speed of light is the same in every inertial frame, and that an FTL signal exists. From those two assumptions and nothing else, the equations give you a backward-in-time signaling device. They do not give it to you optionally. They give it to you mandatorily. Tolman, in 1917, said this in different language but with full clarity. Einstein, 10 years earlier, in 1907, in a paper published in the Yearbook of Radioactivity and Electronics, had already noted that any signal exceeding c would produce consequences violating causality. Einstein did not press the point in detail. He was busy that decade, developing general relativity. Tolman pressed it for him in a textbook, on 2 pages, with a clean construction that a reader could follow without specialized mathematical training. The result is unbreakable. Benford, Book, and Newcomb generalized it in 1970 in the journal Physical Review D, Volume 2, page 263, in a paper titled WC, with characteristic physicist humor, the tachyonic antitelephone. They showed the paradox is robust to any reasonable detector design and signal type. Riccami, in a long review in 1986 in the Italian journal Rivista del Nuovo Cimento, surveyed every attempt that had been made up to that point to construct a paradox-free version of FTL signaling within special relativity. None of them survived. Liberati, Sonego, and Visser, in 2002, published a paper called Faster Than C Signals, Special Relativity and Causality in Annals of Physics, Volume 298, page 167. They confirmed the result for any signaling that exceeds the local speed of light. The Tolman paradox is, at this point, one of the most thoroughly stress-tested results in theoretical physics. It is not going anywhere. There is exactly one escape hatch called the reinterpretation principle, proposed by Gerald Feinberg in 1967 in a paper in Physical Review 159, page 1089. The idea is that you simply reread backward-in-time signals as forward-in-time antisignals. A positive energy tachyon going backward in time looks the same, from the perspective of the equations, as a negative energy antitachyon going forward in time. The reinterpretation makes the equations consistent. It also destroys the ability to use the signal as a controllable communication channel. You cannot send a message with the device, because the moment you try to use it as a phone, the reinterpretation principle reinterprets your message as something nobody sent. The escape hatch closes any usefulness you would have wanted from the FTL transmitter in the first place. Hold the moment. We have set up the apparatus. We have walked through the geometry. We know the equations say the reply arrives before the original signal. We know the result is unbreakable. We know the only escape hatch destroys the very property that would have made FTL communication useful. In the next part, we are going to push the button. Part 6, Signal 1, Signal 2, and the reveal. You are sitting at the controls of a faster-than-light transmitter. Earth's clock reads 0. There is a starship 4 light hours away, moving at 3/4 of C. Outside your window, the sky is black and the console is calm. You reach for the button. You think about pressing it. Your hand approaches the button, and the indicator light blinks. The reply has arrived. You check the timestamp on the incoming reply. It reads -4 hours. The reply arrived at the console 4 hours ago by Earth's clock. 4 hours before you reached for the button. You have not pressed it yet. The reply is sitting on the console anyway. Your hand hovers over the button. You read the message. It says, "I received your signal, the signal you have not sent yet, the signal you are, at this moment, about to decide whether to send." You think for a moment. The reply contains information that depends on the original signal. You have not sent the original signal yet. You are still deciding whether to. If you decide not to send the signal, the reply was triggered by a signal you never sent. If you decide to send the signal, the reply is consistent with what you are about to do, but the reply is already on the console. It arrived 4 hours ago. Whichever choice you are about to make, the reply has already been made on the assumption of one of them. Pull yourself out of the desk for a moment and look at what just happened from a wider angle. The Tolman device gave you the temporal architecture of the grandfather paradox without having to invoke wormholes or warp drives or any other exotic geometry. 2 inertial frames in special relativity plus a superluminal transmitter plus the Lorentz transformation. That is enough to give you a backward-in-time signaling channel. The grandfather paradox is not a quirk of time travel narratives. It is what the equations of special relativity predict the moment you allow signals to exceed C. The architecture is the same. A future event is reaching into the past and modifying it. This is the result that has sat at the foundation of theoretical physics in plain view for over a century. Most people have never heard it stated cleanly. The popular framing has been that the speed of light is a kind of cosmic governor, a reason your starship cannot accelerate fast enough to break the barrier. That framing is correct as far as it goes, and we walked through it in the opening of this video. But it is not the underlying version of the limit. The underlying version is what we have just shown. Faster than light is time travel. The two are the same machine. There is no version of FTL that is not also FTL into the past. The geometry of spacetime, as confirmed by every clock in every laboratory in every country, makes them identical. A device that signals faster than C is, in some other observer's frame, a device that signals backward in time. And that other observer's frame is not exotic. It is just any frame moving fast enough relative to the first. Now, I want you to think about what this means for your everyday life. The chair you are sitting in, the clock on your bedside table, the conversation you had this morning, all of these depend, quietly, invisibly, on no signal having ever crossed this boundary. Your entire life, every thought, every plan, every memory of yesterday and intention for tomorrow has been resting on the fact that the universe has never, in your immediate vicinity, allowed any device to exit the light cone. The constraint is not abstract. The constraint is the structure of having a past at all. If FTL signaling were possible even by one device, one time, one signal, every transmission would be a potential paradox. Every reply would be a potential grandfather. The structure of memory, the architecture of decision, the relationship between cause and effect would not survive contact with a working Tolman device. You would not be able to know whether the message you just received was the result of something you did, something you will do, or something you decided not to do because of the message. The conversation would unravel into a knot. This is why the speed of a light limit is not engineering. The engineering version, the kinetic energy diverging at c, is real, but it is downstream. It is the surface manifestation of a deeper geometric requirement. The deeper requirement is that the universe must keep the order of cause and effect intact. To do that, no signal anywhere in the universe is permitted to cross the boundary between past and future. The boundary is the light cone. The slope of the light cone is c, and the speed of light is, fundamentally, the universe enforcing its own causal contract. A common objection arrives at this point. If FTL signaling is genuinely impossible, why do the equations of general relativity allow you to write down spacetime's Alcubierre warp drives, Morris-Thorne wormholes, Gödel-rotating universes that contain closed time-like curves? Why is the mathematics not stricter about what it permits? The honest answer is that the mathematics is not stricter because it is incomplete. The equations of classical general relativity allow these geometries to exist as solutions on paper. The question of whether they can exist in nature is a different question, one the math by itself cannot answer. It depends on quantum gravity, on the back reaction of matter and energy in extreme curvature regimes, and on physics we have not yet derived from first principles. The classical general relativistic picture is silent on whether time machines are forbidden. It is the modern combination of general relativity with quantum field theory that hints at a forbidding mechanism. Another objection: if FTL is impossible, what is the point of even discussing it? Why not stop there? The point is that the impossibility is not obvious. The Tolman result is not something physics teachers usually walk through in undergraduate classes. It is not what most people think of when they think of the speed of light limit. The underlying version of the limit that FTL is time travel and time travel is paradox is the actual reason the universe is the way it is. And once you understand that, you understand that nobody is ever going to crack the speed of light barrier in the way science fiction imagines. Not because the barrier is too hard, because the barrier is the wall around the very idea of having a story to tell. So the question is no longer whether we can build a faster-than-light transmitter. The question is why the universe seems so determined to make sure we cannot. And the answer to that question, when you actually go and look at the physics, turns out to be the strangest defense mechanism anyone has ever proposed for any system anywhere. We are going to look at it, but before we do, there are still some loopholes the physics has been chewing on for half a century. Loopholes that, if any of them worked, might just slip you past the Tolman paradox without crossing it. Wormholes, warp drives, quantum entanglement, cosmic expansion. In the next part, we are going to walk through them, one by one, and I want you to watch what happens to each of them when you look closely. Part 7. But what about warp drive? The most common, most intelligent, most well-informed objection to everything we have just walked through goes like this. The Tolman argument assumes flat Minkowski spacetime, the kind of geometry you get when there is no significant gravitational curvature, no warping, no folding. But general relativity, which Einstein finished in 1915, allows spacetime itself to be curved. It allows space to bend, twist, and even fold back on itself. So could you carve out a region of curved spacetime where, locally, light still travels at c, but where the region itself moves through the surrounding space at a speed faster than c? Could you, in effect, surf a wave of warped geometry, that is, by the standards of an outside observer, going faster than light, even though nothing inside the wave is locally exceeding c? This is the warp drive idea, and it is more serious than people think. The story of how it became serious starts with a Mexican theoretical physicist named Miguel Alcubierre. In 1993, Alcubierre was a graduate student at Cardiff University in Wales, working on his PhD in numerical relativity. He had been watching Star Trek, the original series, and he had been wondering whether the warp drive his television showed was just sci-fi nonsense, or whether the equations of general relativity actually permitted such a metric. He sat down and did the calculation. In 1994, he published a paper titled The Warp Drive, Hyperfast Travel Within General Relativity in the journal Classical and Quantum Gravity, Volume 11, page L73. The paper was short, about 5 pages. The result was extraordinary. Alcubierre showed that you could write down a metric, a precise mathematical specification of curved spacetime in which a bubble of flat space, large enough to hold a starship, could move through the surrounding universe at any speed you liked, including arbitrarily greater than c. Inside the bubble, an observer would feel no acceleration. Outside the bubble, the surrounding space would be contracting in front and expanding behind, like a wave. The starship would not be moving through space. Space itself would be moving the starship. The Alcubierre metric is a real solution to Einstein's equations. It is mathematically valid. The equations do not tell you it cannot exist. But there is a catch, and it is a big one. The Alcubierre solution requires negative energy density. It violates what physicists call the weak energy condition, the dominant energy condition, and the null energy condition, 3 of the most basic assumptions about what kinds of matter and energy can exist in the universe. To make an Alcubierre warp bubble work, you would need exotic matter with a negative energy density of a kind we have never observed and have no plausible mechanism for creating. In 1997, Michael Fenning and Lawrence Ford did the calculation on how much exotic matter you would need. They found that a working classical Alcubierre bubble, sized large enough for a starship and capable of meaningful FTL travel, would require negative energy roughly equivalent to 10 billion solar masses, 10 billion suns, converted into negative energy. The original Alcubierre drive of the 1990s was beautiful as the math was, an engineering impossibility. There was simply no way to source that much exotic matter. For about 15 years, the warp drive was a curiosity. Cool math, no path to construction. Then, around 2021, something changed. A research group at the University of Göttingen in Germany, led by Alexei Bobrick and Gianni Martir, posted a paper to the arXiv preprint server, archive number 2.102.06824, titled Introducing Physical Warp Drives. Bobrick and Martir showed something that the field had not appreciated. The Alcubierre metric was just one specific example of a much larger family of warp metrics. And within that family, there were warp metrics that could be sourced by purely positive energy density. They did not require exotic matter at all. They required only the kind of stress energy you can build out of ordinary matter and ordinary fields. The catch with these new metrics was that they were, in their first form, subluminal. They warped space, but the bubbles could not exceed the speed of light relative to the surrounding spacetime. They were not faster than light drives. They were, more accurately, geometric propulsion systems that did not violate energy conditions. Still, the proof of concept was important. It showed that the warp metric concept does not necessarily require exotic matter. The math is more permissive than the original Alcubierre solution suggested. In the same year, 2021, Eric Lentz at Göttingen published an independent solution, Soliton class warp metrics, sourced by purely positive energy density. Different mathematics from Bobrick and Martir, but the same general result. You could warp space without negative energy. The frontier was moving. In 2024, the Göttingen team published the most significant paper yet in this lineage. The paper, by Jared Fuchs, Christopher Helmerich, Alexei Bobrick, and Gianni Martir, appeared in Classical and Quantum Gravity. They demonstrated a constant velocity subluminal warp drive solution that satisfied all energy conditions using a stable matter shell. It is the most engineering feasible warp metric anyone has ever derived. It does not require exotic matter. It does not require negative energy. It uses normal matter in a particular geometric configuration, and it produces a real warp effect. I want you to hear that clearly, because the popular narrative around warp drives is that they are pure science fiction. They are not. The modern theoretical physics literature, as of right now, contains positive energy warp metrics that do not violate any known energy condition and that, in principle, could be built out of ordinary matter. The math is real. The papers are peer-reviewed. So the question that matters is, do these new positive energy warp drives actually break the speed of light? Do they let you go faster than c? And the answer is no. Every demonstrated positive energy warp solution to date is subluminal. They warp space without exceeding c relative to the surrounding spacetime. The faster-than-light Alcubierre regime, the regime that would make warp drive a stars-in-a-lifetime technology, a Proxima Centauri by Tuesday technology, still requires negative energy. The honest engineering frontier of warp drive is impressive, but it stays inside the cone. This matters because of where it puts the loophole. If you are trying to use warp drive to escape the Tolman paradox, you need a faster-than-light warp drive. And every faster-than-light warp metric we know of either violates energy conditions in ways that make it physically unrealizable, or, and this is the punchline, reproduces the Tolman paradox exactly. In 1996, and again in 1997, Alan Everett and Thomas Roman, working separately and together, asked the question I would have asked. What happens if you put two faster-than-light Alcubierre bubbles in a Minkowski background and have them exchange signals? They derived the answer. The geometry reproduces the Tolman paradox exactly. A faster-than-light warp drive is, by construction, a Tolman device. The bubble is just hardware around the same geometric impossibility. You can dress the apparatus up in general relativistic curvature. You cannot escape the fact that the moment something exits the light cone, the order of events becomes frame-dependent in a way that allows backward-in-time signaling. So, the warp drive has been the most modern, most serious technical attempt to find a loophole in the speed of light limit. It has been refined for 32 years by very smart people in major universities. Every refinement that keeps the warp drive subluminal is engineering progress that does not threaten causality. Every extension that pushes the warp drive past c reproduces the Tolman paradox. The frontier is real, but the frontier is inside the cone, not outside it. And there is one more wrinkle worth mentioning. There has been some recent activity of contested status around microscale warp bubble experiments. A research group associated with the Eagle Works laboratory at the NASA Johnson Space Center, led by Harold White, reported in 2021 and 2022 anomalous force signatures from microscale apparatuses they described as warp bubble lab analogues. The reports were preliminary. They have not been independently replicated. The peer-reviewed status of the work is uncertain. I am not telling you this because I think NASA has built a working warp drive. I am telling you this because the popular media occasionally picks up these reports and runs with them, and you should know they exist while also knowing they have not been confirmed. The honest assessment is that the theoretical warp drive lineage is more promising than it was 10 years ago, and that no working warp drive micro or macro, lab scale or starship scale has yet been demonstrated. The takeaway is the takeaway we keep arriving at by every route we try. The most sophisticated geometric tool we have ever built for getting around the speed of light limit is warp drive. And warp drive, when honestly extrapolated to faster-than-light regime, gives us a time machine. The same Tolman paradox reappears in a different costume on the other end of the calculation. If even our most sophisticated geometric tools cannot give us a faster-than-light drive without giving us a time machine, what about the other classic loophole? What about the wormhole? What about the spooky correlations of quantum entanglement? What about the way space itself is expanding faster than light, even now at the cosmic horizon? In the next part, we are going to sweep through every loophole that has ever been proposed. And I want you to notice something as we go. Every single one of them, when examined carefully, either does not transmit information or reproduces the time travel problem. There are no exceptions. The universe is being suspiciously consistent. Part 8. The other loopholes fail too. There are roughly 5 major candidates that get raised whenever someone is trying to find a way around the speed of light limit: wormholes, quantum entanglement, cosmic expansion, reported anomalies like the opera neutrino result, tests of Lorentz invariance at extreme energies. Each of these has had moments where someone, somewhere, thought a real loophole had opened. And in every single case, the loophole has either been a misunderstanding of what the data was actually showing, or a path that, on careful inspection, reopens the time travel problem we just laid out. Let me take them in order. The wormhole loophole goes back to a paper published in the American Journal of Physics, volume 56, page 395, in 1988. The authors were Michael Morris and Kip Thorne, 2 of the most important relativists of the 20th century. The paper was the first detailed analysis of traversable wormholes as solutions to general relativity. A traversable wormhole, in the Morris-Thorne picture, is a topological feature of spacetime, a tunnel connecting 2 distant regions of space that you could in principle pilot a starship through. You go in one mouth, you come out the other, and the trip through the tunnel takes much less proper time than it would have taken to travel through ordinary space. The Morris-Thorne wormhole was a real solution to Einstein's equations, in the same sense that the Alcubierre-Watt metric is. The catch was the same catch. You need exotic matter, negative energy density, to hold the throat of the wormhole open. Without exotic matter, the throat would collapse before any starship could pass through. Later that same year, Morris, Thorne, and Ulvi Yurtseva published the follow-up paper that should have ended the wormhole as FTL conversation. It appeared in Physical Review Letters, volume 61, page 1446, with the unmistakable title Wormholes, Time Machines, and the Weak Energy Condition. Their result was elegant and devastating. Take a traversable wormhole, move one of its mouths relativistically, then bring it back. The geometry of the wormhole, with one mouth time-dilated relative to the other, becomes, mathematically, a closed time-like curve. The wormhole has become a time machine. The proper time on the moving mouth is less than the proper time on the stationary mouth, and the 2 mouths are connected by a tunnel of negligible internal length. So you can step into the moving mouth, exit through the stationary mouth, and arrive in your own past. The wormhole is not a separate loophole. It is the same loophole as the Alcubierre warp drive, dressed up in a different topology. Both rely on general relativistic curvature to evade the speed of light limit, and both, when pushed hard enough to actually break the limit, reopen the Tolman paradox. The wormhole inherits the time travel problem the same way the warp drive does, because both are general relativistic dressings on the same kinematic argument that Tolman made in flat spacetime in 1917. Visser, in 1995, published a comprehensive monograph titled Lorentzian Wormholes, From Einstein to Hawking, summarizing 2 decades of research on the geometry. His conclusion was the conclusion that has held since: wormhole-based FTL and wormhole-based time travel are the same problem, and any geometry that allows the first allows the second. There has been more recent work, Maldacena, Malekin, and Popov in 2018, and Maldacena and Chi the same year, exploring traversable wormholes that arise from quantum entanglement structure rather than exotic matter. The energy condition violations get softened in the quantum versions, but the causality preservation is still enforced. The geometric configuration that would allow FTL signaling between mouths is exactly the configuration that fails to form. The universe seems to know what it is doing. Now to the second loophole. quantum entanglement. This is the loophole that gets the most attention in popular science, because it sounds like the strongest case for FTL signaling. And it is half right. In 1964, John Stuart Bell, an Irish physicist working at CERN, published a paper in the journal Physics, Volume 1, page 195, titled On the Einstein-Podolsky-Rosen Paradox. Bell's theorem is one of the most important results in the foundations of quantum mechanics. It demonstrates that quantum mechanics is incompatible with what physicists call local realism, the idea that physical objects have definite properties and that influences propagate at finite speed. Bell's theorem turns the Einstein-Podolsky-Rosen thought experiment from 1935, Einstein's objection to quantum non-locality, into a testable prediction. Bell showed that the quantum mechanical correlations between entangled particles are stronger than any local realist theory can produce. So, if quantum mechanics is right, the universe is not locally realist. Bell tests have been performed dozens of times since. The Aspect-Clauser-Zeilinger experiments from 1972 through 1982 showed that quantum mechanics wins, but with experimental loopholes that critics argued left room for local realist alternatives. In 2015, 3 independent groups closed the last major loopholes. Henson and colleagues at Delft, in a paper in Nature Volume 526, performed a loophole-free Bell test using nitrogen vacancy centers in diamond. Justina and colleagues in Vienna, and Schaum and colleagues at NIST, performed loophole-free tests with photons. All 3 confirmed quantum non-locality at high statistical significance. The 2022 Nobel Prize in Physics went to Aspect, Clauser, and Zeilinger for their pioneering work. So quantum entanglement is real. When you measure one of an entangled pair of particles, the other particle's state appears to update instantaneously, regardless of distance. Faster-than-light correlation is a fact of the universe. It has been measured. It is not in dispute. But, and this is the entire point of the loophole not being a loophole, the no-communication theorem, proved by Philippe Eberhard in 1978 and reformulated by Girardi, Rimini, and Weber in 1980, demonstrates that this faster-than-light correlation cannot transmit usable information. Alice and Bob, separated by light years, share an entangled pair. Alice measures her particle. Bob's particle's state, in some sense, responds instantaneously. But, and this is the cleverness of how the universe handles it, the actual outcomes Bob sees, statistically, are exactly the same regardless of what Alice does. Alice cannot encode a message in her choice of measurement, because Bob's data does not change in any way that depends on her choice. The correlations are real. The signaling is forbidden. This is the universe's subtle bookkeeping. It allows correlations across space-like separations, otherwise quantum mechanics breaks. It forbids signaling across them, otherwise causality breaks. The 2 requirements live in delicate balance, and the speed of light limit is the seam where they meet. Some theorists, including Sabine Hossenfelder and Tim Maudlin from different angles, have argued that this balance may be exactly what enforces the speed of light limit at the deepest level. Whether they are right is an open question. What is not open is the empirical fact that you cannot use entanglement to build a Tolman device. The no-communication theorem is closed. Now to the 3rd loophole, cosmic expansion. This is the one that confuses physics students more than any of the others, because it sounds like it directly contradicts the speed of light limit. Galaxies very far away from us, beyond what cosmologists call the Hubble sphere, are receding from us at apparent velocities greater than c. The Hubble sphere, the distance at which the recession velocity equals c, sits at about 14.4 billion light-years out. Galaxies beyond that are moving away from us in the standard cosmological framework at speeds greater than c. How is that allowed? The answer is that those galaxies are not moving through space at speeds greater than c. They are at rest, locally, in their own corner of the universe. What is happening is that the metric of space itself is stretching, and the metric stretches at all scales the further away 2 points are, the faster the space between them is growing. No information is being transmitted. No light cones are being violated. The galaxies and we are sitting still, locally. The space between us is expanding. The cosmic event horizon, 16.5 billion light-years out, which we covered in detail in our previous Sundown Science video on the edge of the universe, is a horizon precisely because the Tolman geometry is being respected. Signals sent today from beyond it can never reach us. Signals we send today cannot reach receivers beyond it. Cosmic expansion is not violating the speed of light limit. It is the universe demonstrating its commitment to causality at the largest scale it has access to. The expansion looks like FTL only when you misunderstand what kind of motion it is. It is metric expansion, not signaling. The same caveat applies to inflation. The brief epoch in the very early universe, between about 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang, when regions of space inflated apart at vastly superluminal, apparent rates. Same answer, metric expansion, not signal propagation, the light cones held. And it applies to the phase velocity versus group velocity distinction in dispersive media. The phase velocity of a wave can exceed c in certain media without information transfer. The signal front, the leading edge that actually carries information, always travels at less than or equal to c. Sommerfeld and Brillouin worked this out in 1914. The mathematics has been understood for over 100 years. Now the fourth loophole. The Opera neutrino result. In September of 2011, the Opera experiment, located at the Gran Sasso laboratory in Italy and receiving neutrino beams from CERN, announced that the neutrinos were arriving about 60 nanoseconds ahead of light. The headlines were enormous. Some physicists were excited, most were skeptical. They were right to be skeptical. In February of 2012, the Opera collaboration identified the source of the anomaly, a loose fiber optic cable in the timing system connecting a GPS receiver to the master clock of the Opera detector had introduced a 60 nanosecond timing error. With the cable corrected and the timing recalibrated, the neutrinos were on time. They were traveling at very close to c, exactly as expected for low-mass particles. The result was retracted. The collaboration spokesperson resigned. The Opera episode is, in retrospect, a parable about how strong the speed of light limit actually is in practice. The system is so precise that a loose cable producing a 60 nanosecond timing error was, briefly, the best evidence we had ever generated for superluminal motion. The error, when corrected, confirmed what every other experiment had already shown, that c is the same for everyone, every photon, every neutrino, every signal. The fifth loophole. Tests of Lorentz invariance at extreme energies. Some quantum gravity proposals, including certain branches of loop quantum gravity and certain string theory landscapes, suggest that at energies close to the Planck scale, about 10 to the 19th GeV, an energy unimaginably greater than anything any human accelerator can reach. Spacetime itself may become discrete, and Lorentz invariance, the symmetry that gives us the speed of light limit, may be subtly broken. If this is true, you might expect to see energy-dependent variations in the speed of light when you look at very high-energy photons crossing very long distances. We have looked. The Fermi Gamma-ray Space Telescope observed the gamma-ray burst designated GRB 900510 in May of 2009. Abdo and colleagues, in a paper in Nature Volume 462, page 331, used the timing of the gamma rays from this burst to constrain any energy-dependent dispersion of light to better than 1.2 times the Planck mass. Lorentz invariance survives. The MAGIC telescope collaboration observing high-energy gamma rays from the blazars Markarian 421 and Markarian 501 has tightened the bound to parts in 10 to the 19th in relative terms. The Wolf and colleagues' 2003 experiment with cryogenic sapphire oscillators bounded the change in C divided by C at less than 6 parts in 10 to the 12th. Muller and colleagues in 2007, using rotating optical resonators in a Michelson-Morley setup, tightened that to less than 1 part in 10 to the 18th. Every one of these tests is the universe being asked, in increasingly extreme conditions, is the speed of light really exactly the same for every observer and every photon energy and every direction in space? Every test comes back, yes, to a precision that gets more absurd every decade. The speed of light limit is not just enforced. It is enforced with extraordinary regularity at every scale we have managed to probe. And there is one more recent confirmation worth mentioning. The gravitational wave event, GW 170817, in August of 2017, was the first joint detection of gravitational waves and light from a single astronomical event, a neutron star merger 130 million light-years away. The gravitational waves and the gamma rays arrived at Earth within 1.7 seconds of each other after travelling for 130 million years. From this, physicists were able to constrain the speed of gravity to equal the speed of light, to 1 part in 10 to the 15th. Gravitational signals also obey C. Every door we have tried to pry open leads back to the same hallway. Wormholes, warp drives, entanglement, cosmic expansion, opera neutrinos, Lorentz violating quantum gravity. Every loophole is either an optical illusion that does not move information, or a path that, on closer inspection, opens a door to time travel that the universe seems to seal up before anyone can use it. So who is doing the sealing? The universe does not seem to permit FTL. The math of general relativity does not strictly forbid it. The geometries exist on paper. But every time we try to actually build the apparatus, something stops us. Either the energy conditions exclude it, or the no communication theorem defangs it, or the geometric construction, when extended honestly to true FTL, reopens the Tolman paradox. In the next part, we are going to look at the strangest answer anyone has ever proposed for why the universe behaves this way. Stephen Hawking called it the Chronology Protection Agency. And you should know that Hawking proposed it not as a metaphor, but as a serious physical mechanism, with calculations that suggest the universe itself may be actively and forcibly preventing time machines from forming. Part 9. Hawking's Chronology Protection Agency. In 1992, Stephen Hawking published a paper in Physical Review D, volume 46, page 603. The title is one of the strangest titles a paper in fundamental physics has ever carried. He called it the Chronology Protection Conjecture. The paper is 14 pages long. It begins, more or less, with a question Hawking framed in the simplest possible language. He asked, in effect, why has no one ever come back from the future? If general relativity allows closed time-like curves, if the equations permit time machines on paper, and if the universe is old enough and the equations have had enough opportunity to be solved, why have we never observed a time traveller? Hawking's answer was a conjecture, not a theorem. A conjecture is a target, a hypothesis you organize a research program around until either someone proves it or someone disproves it. Hawking's conjecture was that the laws of physics conspire to prevent the formation of closed time-like curves on macroscopic scales. The universe, in this view, has a built-in defense mechanism against time machines. He used the phrase, with characteristic dry humor, to keep the universe safe for historians. To understand why he proposed this, you need to understand the situation he was responding to. By 1992, theoretical physicists had been finding solutions to Einstein's equations that contained closed time-like curves for over 40 years. Kurt Gödel, the Austrian mathematician, who, in 1931, had shattered the foundations of formal logic with his incompleteness theorems, published a solution in 1949 that he gave to Einstein as a 70th birthday gift. The Gödel universe was a rotating universe, and in it, every observer's world line could be deformed, with enough fuel and a strong enough rocket, into a closed loop in time. You could fly out, travel for a while, and arrive at your own birth. The Gödel universe, as far as Einstein's equations were concerned, was a perfectly valid solution. It was just that, as far as we knew, our universe was not the Gödel universe. The actual universe is not rotating fast enough to permit the Gödel construction. But in 1974, Frank Tipler showed that an infinite rotating cylinder could host closed time-like curves in any spacetime, regardless of whether the universe as a whole was rotating. In 1988, Morris, Thorne, and Yurtsever showed that traversable wormholes could be turned into time machines by relativistically moving one mouth. The Kerr metric, the spacetime around any rotating black hole derived by Roy Kerr in 1963, contains closed time-like curves inside its inner horizon. The mathematics of general relativity does not forbid time travel. The mathematics of general relativity makes time travel surprisingly easy to write down. So Hawking, in 1992, was responding to a strange situation. The classical theory was, by the standards of mathematics, almost too permissive. It allowed configurations that, if they could be physically realized, would let observers visit their own past. And the only thing standing between the equations and the world was the apparent fact that nobody had ever built one. Hawking's proposal, maybe the classical theory is incomplete. Maybe quantum effects, layered on top of the classical geometry, conspire to destroy any region in which a closed time-like curve begins to form. The proposed mechanism was specific. Quantum field theory in curved spacetime predicts that the vacuum has what physicists call a stress-energy tensor, a kind of pressure and density of empty space itself. When you have a smooth, well-behaved background spacetime, the vacuum stress energy is small and finite. When you approach a region where closed time-like curves are about to form what relativists call the Cauchy horizon, the boundary between the chronology-preserving region and the chronology-violating region, the calculations show that the vacuum stress energy diverges. The vacuum near a forming Cauchy horizon generates effectively unbounded back reaction. The picture, in physical terms, is this. Vacuum fluctuations, the random virtual particles popping in and out of existence that characterize empty space at the quantum level, normally exist for vanishingly short times before they re-annihilate. But in the presence of a forming closed time-like curve, the same fluctuation can travel through the loop and meet itself. It can amplify itself recursively. Each pass through the loop multiplies the energy density. The vacuum in the vicinity of the would-be time machine becomes, in effect, an exponentially diverging source of stress energy. The metric warps. The geometry destabilizes. The would-be time machine destroys itself before causality can be violated. Several independent calculations by different groups using different approaches have produced this same general result. Frolov in 1991, Kim and Thorne in 1991, Hiscock and Minkowski as far back as 1982. All of them found that the back reaction near a forming Cauchy horizon is divergent. They all used different specific configurations, different spacetimes, different field theories, but the result was the same. The would-be time machine self-destructs. I want you to picture what this means concretely. Imagine you are an engineer who has solved the impossible. You have lined up your wormhole mouths or your warp metric or your tachyonic transmitter. You have everything in place. You activate it. In the microsecond, before the closed time-like curve forms, the quantum vacuum near your apparatus begins to oscillate. Vacuum fluctuations, normally bounded and tiny, begin to amplify themselves through the would-be loop. The energy density rises. The metric warps. Before the loop can close, before causality can be violated, your machine is destroyed by the universe's own quantum fields, tearing it apart from inside. Hawking's framing of this was the line that gave the conjecture its name. He proposed that the laws of physics contain something like a chronology protection agency, which prevents the appearance of closed time-like curves and so makes the universe safe for historians. It is one of the most remarkable propositions in modern theoretical physics. The universe, in Hawking's picture, is not just neutral about whether time machines exist. It is actively defensive about it. There is, embedded in the structure of quantum fields in curved spacetime, what amounts to an enforcement mechanism. The laws are not silent on the question of FTL. They are forbidding it, with calculations behind them. The status of the conjecture, as of right now, is that it is alive but not closed. Matt Visser, in 2002, published a survey paper called The Quantum Physics of Chronology Protection. His conclusion was that the computed back reaction effects are real, but their interpretation depends on assumptions about quantum gravity that are themselves not nailed down. Some authors, Maeda, Ishibashi, Narita, have argued that the back reaction is generic and that chronology protection should be considered a robust feature of any sensible quantum theory of gravity. Others have constructed counterexamples in specific geometries where the divergence is not as clean as the general case suggests. The conjecture has not been proven as a theorem, but it has not been disproven either, and most physicists who work in this area treat it as a working hypothesis that something like it is correct. There is an alternative reading worth knowing about, because it points to a slightly different answer to the same question. In 1989, the Russian physicist Igor Novikov proposed what is now called the Novikov self-consistency principle. Friedman, Morris, Novikov, Thorne, and Yurtsever expanded the idea in 1990. In Physical Review D, Volume 42, page 1915, in a paper titled Cauchy Problem in Spacetimes with Closed Time-like Curves, the Novikov proposal is different from Hawking's. Where Hawking suggested an active mechanism that destroys time machines, Novikov suggested a passive selection rule. Closed time-like curves, in Novikov's view, may exist, but the only allowed histories within them are self-consistent ones. The grandfather paradox does not occur because the universe rejects inconsistent solutions outright before any history can unfold inside them. Echeverria, Klinkhammer, and Thorne in 1991 ran a famous calculation called the billiard ball analysis. They asked, take a billiard ball that goes back in time through a wormhole and knocks itself off course before entering. The classical paradox is that if the ball is knocked off course, it never enters the wormhole, so it never knocks itself off course. So it does enter the wormhole, so it is knocked off course, and so on, contradictorily. What Echeverria, Klinkhammer, and Thorne showed was that the billiard ball trajectory has multiple consistent solutions, but no inconsistent ones. The geometry forbids the inconsistency. There are paths the ball can take in which it gives itself a small nudge that it would have taken anyway, without contradiction. The grandfather paradox does not arise. The implication of Novikov's self-consistency, if it is correct, is unsettling in a different way from chronology protection. If chronology protection is correct, time machines cannot form, and free will is preserved, and there is no paradox to worry about. If Novikov's self-consistency is correct, time machines can form, but free will, in any region containing a closed time-like curve, is geometrically restricted in ways the agents inside the curve cannot detect from the inside. The agents would experience their choices as free. The geometry would have already excluded all inconsistent options. Lloyd and colleagues, in 2011, in Physical Review Letters Volume 106, page 040403, derived a quantum mechanical version of Novikov self-consistency, using the formalism of post-selected, closed time-like curves. The work is theoretical. It has not been demonstrated experimentally, but it shows that the self-consistency principle has a quantum extension that is internally consistent. Chronology protection and Novikov self-consistency are two answers to the same question. Why has the universe never produced a working time machine? Either the laws of physics actively destroy any machine that tries to form, or they permit only self-consistent histories that look from the outside like the machine is being prevented. Either way, the speed of light limit holds, because the alternative, a working faster-than-light transmitter, used in a way that produces a paradox, is a world the universe does not seem to allow. Push the implication. The speed of light is not just a number engineers have to outsmart. It is the boundary the universe enforces to keep cause and effect from collapsing into each other. Hawking suggested an active mechanism. Novikov suggested a passive selection rule. Both are answers to the question, why does the universe behave as if FTL were forbidden, even though general relativity does not strictly require it to be? Both involve physics quantum field theory in curved spacetime, or the selection rules of self-consistent histories that go beyond what classical relativity by itself can describe. Something is enforcing the contract. We are not yet sure exactly what. Once you understand that the universe seems to be defending itself against time machines, the question is no longer whether we can build one. The question is why the universe is the way it is in the first place. Why is C, of all numbers, the one that gets defended? What is so special about this particular boundary? That is the question for the next part. And the answers are stranger than the question. Part 10. Why C at all? Nobody in physics disputes that C is constant in our universe. We have measured it to absurd precision, in every direction, at every photon energy, in every laboratory frame. That is settled. The unresolved question, and it is one of the deepest unresolved questions in fundamental physics, is why. Is the speed of light limit a contingent fact about our particular universe? Something that could have been otherwise, the way the mass of the electron or the strength of the strong force could in principle have been otherwise? Or is it a structural necessity of any universe in which observers can think? Is the speed of light something we just happen to find in our local cosmos? Or is it the kind of constraint that any universe stable enough to support memory and prediction would have to enforce? There is no consensus answer. There are several serious readings, each held by serious physicists, each with internal coherence, and none of them yet decisive. Let me walk you through the leading candidates, because they tell you something about how strange a question this actually is. The first reading is what I will call the causalist reading. It traces back through Hermann Bondi, the British relativist, who in 1962 wrote some of the most influential expositions of relativity for working physicists, and through Roger Penrose, whose 2004 book The Road to Reality is one of the most ambitious modern attempts to lay out the structure of fundamental physics. The causalist position is that the structure of the universe is fundamentally a partial ordering of events. For any two events in spacetime, either one definitely precedes the other, or neither does. They are space-like separated, with no causal contact possible. This partial ordering is the primitive fact about the universe, and the speed of light is the slope of this ordering. Causality is not derived from the speed of light limit. The speed of light limit is derived from causality. In this reading, the question, why can we not go faster than light, is misposed. The right question is, why is there a difference between past and future at all? And the speed of light is the answer. It is the geometric expression of what it means for an event to be in your past versus your future versus your elsewhere. If the causalist reading is right, then asking for FTL is asking for a universe without a past. There is no version of the request that grants the speed but keeps the asymmetry. The two are the same thing. The second reading is the information theoretic reading. It traces through John Wheeler, who in 1990 published an influential essay called It from Bit, in which he proposed that the foundations of physics are informational rather than material, that the most basic constituent of reality is not matter, not energy, but bits. The information theoretic reading also draws on the work of Jacob Bekenstein, who in the 1970s derived a fundamental upper bound on the amount of information that can be stored in any region of space, given the energy contained in that region. Bekenstein's bound is connected, through general relativity, to the area of the region's boundary rather than its volume, the result that became, in the hands of Gerard Hooft and Leonard Susskind in the 1990s, the holographic principle. The universe, in this view, is a kind of network of information transfer, and spacetime itself may be emergent from the entanglement structure of an underlying informational substrate. In the information theoretic reading, the speed of light is the saturating bandwidth of this network. It is the maximum rate at which any region of space can communicate with any other region, given the underlying informational architecture. To exceed c would be to exceed the available channel capacity of the universe, to require more bits to be transmitted in a given time than the structure of space can support. The light cone, in this reading, is the universe's bitrate budget. The speed of light is fixed by the holographic bound, and the holographic bound is fixed by the ultimate informational architecture of reality. This reading became more concrete in 1997 when Juan Maldacena published the ADS CFT correspondence, demonstrating mathematically that a particular five-dimensional theory of gravity is exactly equivalent to a four-dimensional quantum field theory living on its boundary. This is the holographic principle in its most precisely formulated form, and in 2010, Eric Valinde published a remarkable paper proposing that gravity itself may be derivable from the information theory of holographic screens. If Valinde is right, gravity is not a fundamental force at all. It is a thermodynamic consequence of how information is stored on holographic surfaces, and the speed of light in this picture would be the maximum rate at which the screens can update. The third reading is the chronology protection reading. We just spent the previous part on it. The speed of light limit is what is left over after the universe has eliminated all of its own contradictions. It is the boundary the universe enforces to prevent itself from collapsing into self-reference. In this reading, c is whatever speed the universe happens to need in order to keep its causal contract intact. The number is set by the requirement that quantum field theory in curved spacetime not produce divergent back reaction near forming closed time-like curves. The number is, in a sense, derived from the universe's self-defense mechanism. I want you to pause for a moment and let the picture settle. The universe has a heartbeat. It is the rate at which causal influence can propagate from one point in space to another, and it is exactly the same in every direction, at every scale, for every kind of signal. Photons in the visible spectrum, from the lamp on your nightstand. Gamma rays from the most distant blazars in the universe. Gravitational waves from black hole mergers a billion light-years away. Gluons binding the quarks in the protons in the iron in the hemoglobin in your blood. Electron transitions in the synapses of every neuron in your brain. All of them are constrained to the same finite bandwidth. The speed of light, 299,792,458 meters per second, is the universal pulse at which causal contact propagates. The universe is not silent. It is humming at exactly that rate in every cubic millimeter of space, at every instant. The constraint is not on your starship. The constraint is on every quantum process in the universe, and your starship would just be one more thing that obeys it. The fourth reading I will call the substrate, or simulationist reading. It is the view, advanced in different forms by Nick Bostrom in 2003 and Max Tegmark in 2014, that the universe may be a computational substrate of some kind, a structure that runs the laws of physics the way a computer runs a program. If that is right, c may be the speed of the simulation's update rule. It is the maximum rate at which information can propagate between neighboring grid cells in the underlying code. There is no going faster because there is no faster part of the substrate. The speed of light is the clock rate of the cosmic computation. The substrate reading is unfalsifiable in its strongest forms. There is no experiment we can run that would tell us whether the universe is a simulation or whether it just happens to look like one. But the reading has the virtue of making the speed of light limit feel less mysterious and more like a feature of the engine. If the universe is a process running at finite update rate, c is just that rate. There is no further puzzle about why it has the value it has. It has the value it has because the substrate runs at that rate. The fifth reading is the many worlds reading, drawing on Hugh Everett's 1957 interpretation of quantum mechanics. In Everett's framework, the wave function never collapses. Instead, every quantum event splits the universe into branches, with all possible outcomes realized in different branches. In a many-worlds universe, FTL signaling and time travel would generate decoherent branchings rather than paradoxes. Closed time-like curves would correspond to particular branches in which self-consistent loops happen to occur. Inconsistent loops would simply not realize as actualized branches. The speed of light limit, in this reading, is statistical rather than absolute, but the statistics are so overwhelmingly weighted that the limit appears absolute to any observer inside any normal branch. I will mention briefly the sixth reading, which is the most marginal but worth knowing about. Variable speed of light cosmology, advanced by John Moffat in 1992 and by Andreas Albrecht and João Magejo in 1999. The proposal is that c may have been larger in the early universe than it is today, and that the apparent constancy is a late emergent property. The motivation is to solve the horizon problem in cosmology, the puzzle of why the cosmic microwave background looks so uniform across regions that should not have had time to be in causal contact. If c was larger in the early universe, those regions could have communicated and equilibrated, removing the need for inflation as the standard solution. The variable speed of light proposal has been marginalized after Planck 2018 confirmed slow roll inflation predictions to high precision, but it is not strictly ruled out, and it serves as a reminder that we cannot simply assume the speed of light limit is necessary. There is a non-trivial possibility that it is contingent, and that we are simply living in a universe whose c happens to take a particular value. So, what do we do with this menu of readings? Physicists do not agree on what the speed of light is. They agree only that it is the boundary across which the universe stops behaving like a universe. The interpretive divide is not cosmetic. It is a divide about what reality is fundamentally for. Is reality a partial ordering of events? An informational network with a finite bandwidth? A defended construction protected by quantum field theory? A process running on a substrate at finite update rate? A statistical sum over branching histories? The data we have is consistent with all of these. The data we do not yet have, and may never have, is what would distinguish them. There is one more empirical fact worth holding on to, because it is one of the strangest things about the speed of light. The same number controls electromagnetism, gravity, and the propagation of changes in the metric of spacetime itself. Three apparently unrelated phenomena, one shared constant. 2/3 of a century of theoretical physics work, string theory, loop quantum gravity, asymptotic safety, causal dynamical triangulations, all of the major contender frameworks for unifying general relativity with quantum field theory has not produced an agreed-upon explanation for why these three should share a single number. We have empirical evidence that they do. We have no first principles derivation of why they must. Whichever reading you favor, you have to confront a strange empirical fact. The constraint is everywhere. The constraint is exact. The constraint is enforced. And we cannot yet say with confidence why. So, what does it cost the universe to keep this number? In the next part, we will look at what it costs you. Part 11. The real cost of crossing it. I want to come back to you, to the room you are in, to your body. The chair you are sitting in is solid because the electrons in its atoms cannot signal each other faster than light. Solidity, the everyday sensation of pressing your hand against a surface and feeling resistance, is electromagnetic. The electrons in your hand and the electrons in the chair repel each other through electromagnetic forces, and those forces propagate at c. Every micro-interaction that gives a chair its solidity is bounded by the speed of light limit. If the limit did not hold, the electromagnetic forces would not propagate consistently, and there would be no consistent solidity. There would not be a chair to sit in. The clock on your bedside table ticks forward because nothing in its workings violates causality. The escapement, the gear train, the second hand sweeping forward in steps, every component depends on causal interactions among atoms, and every causal interaction is bounded by c. If FTL signaling were possible, the clock would not tick consistently. Some of its internal causes would arrive after their effects. The clock would not be a clock. Your own mind, as it follows this sentence, is built out of synapses that fire at speeds bounded by c. The action potentials in your neurons travel at about 100 meters per second, far below c. But the underlying biochemistry is sustained by electromagnetic interactions that propagate at c. The integration of a thought, the binding of a perception, the persistence of a memory, all of these depend on consistent causal sequencing across billions of synapses. The reason your thought has a beginning, a middle, and an end, and the parts are in that order, is that no signal in your brain has ever crossed the boundary that would let the end arrive before the beginning. The speed of light limit is not abstract. It is what is keeping your thought process from collapsing into incoherence. I want to walk you through what it would actually mean to remove the constraint, because the popular framing of FTL travel, the science fiction framing, gets it almost exactly backwards. In the popular framing, the speed of light is a wall around your starship. Cracking the wall would deliver the stars to humanity, trips to Proxima Centauri in an afternoon, Andromeda by next year, the galaxy mapped in a lifetime, a grand unified human civilization spreading across the cosmos. Crack the speed of light limit, and the universe becomes accessible. That is not what the equations say. That is not what would happen. What would actually happen is that the relationship between cause and effect would unravel. Every signal sent would, in some other observer's frame, be a signal sent into the past. Memory would not work because the events your brain is integrating would not have a stable order. Decision would not work because choices and their consequences would loop back on themselves. The conversation between two people would become a knot. The narrative of a human life, the passage from birth through experience to death, would not have a coherent arc. The barrier is not a wall around your starship. It is the wall around your existence as a coherent being. Removing it would not free you. It would erase the difference between the question and the answer. It would dissolve the difference between the deed and the consequence. It would make memory and prediction the same thing, and once those are the same thing, there is no thinking observer to notice. There is a slightly different way to put this. The Tolman device, the wormhole time machine, the FTL warp drive, none of these are devices that defeat the universe. They are devices that, if they worked, would defeat the very property of the universe that makes you possible. The universe has been keeping its causal contract every nanosecond of your life. The contract is what allows there to be a your life at all. I want you to feel that, not as a frightening thought, but as a quiet one. The speed of light is not a wall. It is the price the universe pays to have a past at all. And you, sitting here, breathing, remembering yesterday, planning tomorrow, you are made possible by the fact that this price has been paid every nanosecond, in every cubic millimeter of space-time since the beginning. If you have ever felt a small grief that the stars are unreachable, that the cosmos is too big for us, that the speed of light is a kind of prison, let it go for a moment. The constraint is not what is keeping you from the universe. The constraint is what is keeping you. There is no you in a world without it. The chair you are sitting in is still where it was. The clock on your bedside table is still ticking forward. The conversation you had this morning is still in your past, in the same place it was when you remembered it the first time. The universe is still keeping its contract. The Tolman device, the warp drive, the wormhole, the entangled pair, the chronology protection agent, all of them lead back here, to the chair, to the clock, to your thought following this sentence, possible only because the universe has not allowed any signal anywhere to outrun the boundary that separates this sentence's beginning from its end. That is not a small thing. That is the gift of C. I am going to ask you one more thing. I want you to consider, just for a moment, what it would mean for physics to be able to derive this constraint from first principles. Right now, we cannot. The number 299,792,458 meters per second is empirical. We measured it. We did not derive it. There is no fundamental theory in the year 2026 that tells us this number must be exactly what it is. There are theories, string theory, loop quantum gravity, holographic dualities, that try to explain why there is a finite C at all. None of them yet predicts the specific value. But the universe has chosen one. And every scale of reality, from the binding energies of atomic nuclei to the propagation of gravitational waves across billions of years, agrees on what the chosen number is. The constraint is universal. The constraint is exact. The constraint is enforced. And so we end where we began, with one number defended at every scale, by every field, in every direction. And one final question. The one nobody, not Hawking, not Einstein, not Tolman, has been able to answer. Part 12. The open question. 2.5 hours into a video on the speed of light, here is what we know. We know C is exact, 299,792,458 meters per second, by international definition, since 1983. We know C is the same in every inertial frame, confirmed by every relativity experiment ever performed, from Michelson-Morley in 1887 through to the high-precision atomic clock experiments at NIST and GELA in the 2020s. We know C is the boundary between past and future. Faster-than-light signaling, as Tolman showed in 1917, would convert any inertial frame disagreement on simultaneity into an explicit closed loop in time. There is no version of FTL signaling that does not also violate causality. The two are the same machine. We know that every general relativistic dressing of the FTL idea, Alcubierre warp drives, Morris-Thorne wormholes, Kerr-metric closed time-like curves, Gödel rotating universes, inherits the same causality problem. Either the geometry requires exotic matter that does not appear in nature, or the geometry, when honestly extended to FTL regime, reproduces Tolman's paradox. We know quantum entanglement does not provide a loophole. The no-communication theorem, proved by Eberhard in 1978, ensures that quantum non-locality cannot transmit usable information. Cosmic expansion does not provide a loophole. The metric expands, but no signal exits the cone. Opera neutrinos did not provide a loophole, a loose cable, in 2011. gave us our briefly best evidence for FTL, and the cable was loose. Lorentz invariance precision tests have, every decade, tightened our bounds on possible deviations from the speed of light symmetry, and every test has come back consistent, with no deviations to absurd precision. We know that Hawking, in 1992, conjectured that the universe contains an active mechanism, quantum field theory, in curved spacetime, generating divergent vacuum back reaction near forming Cauchy horizons that physically prevents time machines from forming. We know the calculations behind the conjecture have been done by multiple groups using different methods, and they all suggest the back reaction is real. We know we have not yet proved chronology protection as a theorem. We know there is an alternative reading Novikov self-consistency, in which the universe permits closed time-like curves, but allows only self-consistent histories within them. We know these readings are not mutually exclusive, and that physics has not yet decided between them. We know that C controls electromagnetism, gravity, and the propagation of changes in the metric of spacetime itself. We do not know why. We know there are 5 major interpretive readings of what the speed of light limit is fundamentally causalist: information theoretic, chronology protection, substrate, many worlds, and we have not chosen between them. We know variable speed of light cosmology has been marginalized but not eliminated. We know that the question of whether C is contingent or necessary is among the deepest unresolved questions in fundamental physics. We know that no observation has ever required the speed of light limit to be revised. We know that no observation has ever required Tolman's argument to be reinterpreted. We know that, as of right now, in the year 2026, the speed of light barrier is the most thoroughly tested, most thoroughly enforced, most thoroughly defended boundary in all of physics. What we do not know is the question I want to leave you with. We do not know whether the universe could have been otherwise. We do not know whether a universe with a different C, or no C at all, could in principle have given rise to thinking observers. We do not know whether the speed of light limit is a contingent feature of our particular cosmos, the way the value of the electron mass is, or whether it is a necessary feature of any universe that allows there to be a coherent past for any observer to remember. The answer, if it exists, will come from a deeper theory of quantum gravity than we currently possess. The work is being done right now in research groups at universities and theoretical physics institutes around the world. The answer may come in our lifetimes, it may not. But here is what I find most arresting about all of this. Whatever the answer turns out to be, the speed of light has been doing its job for 13.797 billion years. Every photon emitted in the early universe, the photons that became the cosmic microwave background, has been propagating at exactly c for that entire time. Every atom that exists today, including the atoms in your body, is held together by electromagnetic forces that propagate at exactly c. Every memory you have, every choice you have made, every word in this video, all of them are made possible by the universe's consistent enforcement of one number, one boundary, one slope of the cone, in every direction, at every scale, every nanosecond. The light from Proxima Centauri left 4 years ago. The light from Andromeda left 2.5 million years ago. The light from the cosmic microwave background left 13.797 billion years ago. Every photon arriving at your eye right now is older than every choice you have ever made. The speed of light is not a wall around your starship. It is the medium through which the universe remembers itself. And every star you have ever seen is the universe holding up evidence proof that the contract has been kept. You are made possible by this. The chair you are sitting in, the clock on your bedside table, the conversation you had this morning, the thought following this sentence that you are about to have next. None of it can happen in a universe where the contract is broken. So if you have ever wondered why the speed of light is what it is, why this number, why this constraint, why this barrier we cannot get past here is what I want you to take with you. The universe is not keeping the speed of light to make your life difficult. The universe is keeping the speed of light to make your life possible. The speed of light is what keeps the answer behind the question where it belongs. Sleep well,